Hello, welcome to another video of CS360. All right, so in this video, we'll talk about the halting problem. So in particular, we will show a language that cannot be decided by a Turing machine. So recall, as mentioned in the notes, that we say that the language A is decidable if there is a TM M that always halts and accepts exactly the strings of A. Okay, so in general, if M is a TM, so if M is a TM, the Turing machine, then L of M is the set of all the strings W such that M of W accepts. Okay, but L of M this is called the language of the Turing machine, or the language recognized by the Turing machine. But it's the Turing machine M doesn't have to decide this language. Why? Because although the Turing machine M accepts each string in the language in this language, and this is exactly the language of the strings M accepts, M doesn't necessarily reject all the strings not in this language. So M might run forever on some strings not in the language. So if M always halts, meaning it always either accepts or rejects, then we say that M decides L of M. Okay, so L of M is decidable. Or just in general, language A is decidable if that language A is L of M for some M, and also that M always halts. Okay, so otherwise, if you only have if A is L of M for some Turing machine M, then we say A is recognizable. But this is a weaker property than being decidable. So to be decidable, you have to be recognizable. And also the Turing machine that recognizes the language has to always halt. Okay, so that's fine. So whoops. Okay, so that's fine. So now the claim is going to be that there are some languages that are not decidable, that cannot be, you cannot accept exactly the strings in the language and reject the rest. And that one example of an undecidable language is the halting problem. And the halting problem is this. The halting problem is the set of all pairs of a Turing machine and a string, where we use these angle brackets to note that we converted everything into a string. So set of all pairs such that M of W halts. Oops. So this is an important language because often we would want to know whether a Turing machine M halts on an input W. Okay, and this is basically if and only if this pair MW is in HTM. Okay, so we would want to know whether a string is in HTM or not. This is a common thing we want to know. We want to know whether a machine halts on an input, a given machine halts on a given input. So we would like to decide whether a given string is in HTM, because we would like to know whether a given machine halts on a given input. Okay. So, however, the claim is that HTM is undecidable. Okay, so there's no Turing machine that decided. So let's prove this now. So the proof uses something called diagonalization. Basically, it's kind of a self-referential, paradox of a proof. So let's go through it. So the proof starts by saying, suppose by contradiction that HTM is decidable. Okay, so then let P be a TM deciding it. Okay, so P of MW accepts if M of W halts and rejects if M on W loops. Or again, remember that this terminology looping means not halting. To say that a machine loops an input just means it doesn't halt. Okay, so we're assuming that we have this machine P. It's a Turing machine, and this is what it does. This is its behavior. Okay. Okay, so then what we are going to do is, so we have this machine P. So what we're going to do is define another Turing machine Q. Okay, and here's what Q does. So Q, it expects to take in, well, it takes in a string, but it expects to take in a string that's the code of another Turing machine M. Okay, so or actually let's call it A. So it's expected to take in the code of another Turing machine A. If the input is something else, Q will just reject. So if the input doesn't parse, can't be read as the code of a machine, Q can just reject. Okay, so when Q takes in the code of a machine A, here's what Q is going to do. Q will first run P on A, comma A, basically. It's basically going to feed this pair of A, comma A into P. And then if P accepted, if P accepted, if P accepted, enter an infinite loop. Okay, and then if P rejected, halt. Okay, so we're thinking of P and Q as basically computer programs here. Okay, so P is a computer program that is supposed to take in a pair, kind of MW kind of thing. It's supposed to take in such a pair and tell you whether the code of M, when you run it on the input W, will halt or not. Okay, so P is just a program that's supposed to do that. It takes in code and tells you whether this code halts on a specific input. Okay, that's P. And Q is another program. Q takes in one program, just a single program A, and what it does is it runs P on A, comma A. Okay, and then if P accepts this input, then Q deliberately goes while true or something. It just enters an infinite loop on purpose. Whereas if P rejected, if this run of P rejected, then Q immediately halts. And so now the question is, so this is the definition of Q. We're done defining Q. Okay, so Q, if P is a program that exists, then we can use it to define the program Q. So Q is just a valid program now. Okay, so now the question is, what does Q of Q do? So what does Q do when we feed it its own source code as the input? Okay, so Q is a program that has a source code. Feed Q its own source code as input, press run. What happens? Okay, so what happens? So the first thing that happens is, of course, the first step is this, right? So the first step is to run P of you know, q, comma q, basically. So p is going to run on this. And what does p do? P, so we know that p halt, rather p accepts if this q, this first q, plug in this string, so q run on q, basically, if that halts. Okay, and then p rejects if this doesn't, if this thing loops. So we know that that's what p is supposed to do. That was the definition of p. Okay, so in this first step, this is what happens. P either accepts or rejects depending on whether q of q halts or loops. Now, if p accepted, we're in this case, if p accepted, then q run on q is now going to enter an infinite loop. Except if p accepted, then we know q of q is supposed to halt. Okay, so something is impossible here. So if p accepted, we can show that q run on q. Here a is q, right? We're plugging in a equals q. So here, if the run of q on q here, this run over here, well, if p accepted the pair q comma q, then q run on q will enter an infinite loop, even though p is supposed to halt. So p says it's supposed to halt. Whereas if p rejects, then that means p sort of says that q on q enters an infinite loop. But if p rejects, then q of q in fact halts. Okay, so either way, p couldn't have got the answer right. I mean, if p said one thing, then by definition of q run on q will do the opposite. So it's not possible. P uses the source of, sorry, q uses the source code of p to make sure that p cannot predict the action of q run on q. Okay, and that's the end of the proof. That's the contradiction. So so basically, what does it do? It can't halt. It can't loop, because we get a contradiction in both cases. So contradiction. It has to either halt or loop. So this is a contradiction. Hence, p cannot exist. Okay, so that's it. So this is the proof of the halting problem. It's a very confusing proof, but it's not very kind of long or complicated. It's just a very self-referential and confusing proof. So you can try to go through it. You know, maybe you can even imagine, you know, what p might be. P is, after all, just trying to look at an input program m and an input string w and check whether m will halt on one run on w. So you know, you can imagine various things. Like you can imagine p is trying to look inside the code of m and see whether there are any obvious infinite loops or something, like whether there's a while true in there somewhere. You know, you can imagine various such p's and then see what happens, why that p doesn't work by going through this proof. So by going through what q would be for that, q depends on p. The way we define q depended on p, right? Because q is running p as a subroutine. So for any concrete p, you can check what the corresponding q would be, and then why that p, what happens when q runs on q, when you plug it, when you give q its own source code, what happens, and why p cannot predict it correctly. Okay, so that's the proof that the halting problem is undecidable. Now, once you have a single undecidable language, that especially kind of a nice one like the halting problem, you can prove many other languages are undecidable just using reductions. Basically, this notion that just a proof by contradiction that goes, okay, suppose this one language A was decidable. Suppose we had a Turing machine that decides it, then we could use that to decide the halting problem. But we know that halting problem is undecidable, so we get a contradiction. So this is kind of a good starting point for proving other things are undecidable, basically just by reductions. Basically just saying, if you could decide something else, then you can decide the halting problem. Okay, therefore you couldn't have done that. So you know, this is actually the main way you would prove that languages are undecidable. So you can't do it for, you have to use a different proof technique the first time. But after you have one undecidable language, like the halting problem, you can try to prove a whole bunch of others are undecidable only by converting them to that. Okay, and reduction is a bit of an informal notion. It's just a bit of a kind of an argument by contradiction that says assume by contradiction language A is decidable. Then halting problem would be decidable contradiction. Okay, so that's a bit of, it's any argument of that form. But there's a special case of reductions called mapping reductions, which we're going to define very carefully because it's a convenient notion that comes up. So a mapping reduction between two languages is kind of a special case of this general reduction argument I sketched. And the mapping reduction will get its own notation. So we will say that a mapping reduce. So this is a map reduction between A and B. This less than or equal to with an M subscript. That's an M there. And here A and B are languages. So we say this is true if we can convert instances of A into instances of B. So inputs, we can basically convert the problem A into the problem B. We can sort of take inputs to A, where we want to know whether this input is in A, and convert it into an input that we want to know if it's in B, such that answering whether f of x is in B will tell us whether x is in A. Okay, this is the goal of this reduction, that you can take an input to A and convert it into an input to B. Okay, and so formally, a mapping reduction between A and B, or from A to B, I guess, from A to B, is a function that goes from the alphabet of A to the alphabet of B. So here we're assuming that A is a subset of sigma star and B is a subset of gamma star, which is computable we'll talk about what that means in a second, and such that x is in A if and only if f of x is in B. So in particular, if x is in A, then f of x is in B, and if x is not in A, then f of x is not in B. So both directions have to hold here. Okay. So note that the conversion is only one direction. The conversion is only from inputs that may or may not be in A. Those get converted to inputs that may or may not be in B. Okay, there's no guarantee that you can convert the other way. Okay, but for that one conversion from inputs to A to input to B, then two things have to hold. Both if the input to A it really is in A, then the converted version has to be in B. And if the original thing is not in, the converted version has to not be in B. This way, if you had an algorithm that solves B, that tells you whether strings are in B, suppose you had some algorithm that tells you whether strings are in B, then you can get an algorithm for deciding if strings are in A. And the way you do that is you would start with an input to A, you would start with X. Then you would apply your algorithm that computes f of x. So you would have to be able to compute f of x. And then you get the string f of x. And then you apply your algorithm for deciding whether it's in B. And that tells you whether the original was in A. So now, if this new string f of x is in B, then you can just say, yep, the original string x was in A. And if it's not in B, you can say, nope, the original was not in A. Okay, so, and the key thing is here, the key condition on f, other than this requirement over there, is that f has to be computable, which means there must be a Turing machine that computes f. So what does it mean for a Turing machine to compute f? So we say basically, so we say f is computable. Computable if there is a Turing machine that computes it. When let's call the string machine M. The string machine is going to be M. So when M is run with X on the tape, M halts with f of X written on the tape. Okay, so we're going to run M with this input X on the tape. So that's the input to M. And M will, let's say it will accept. I mean, it doesn't matter if it will accept or reject, but it will halt. It will accept, say. And when it does accept, then f of X is what's written on the tape. So basically, it's kind of a way for the Turing machine to output something, is to write it on the tape. So M will erase X and write f of X instead on the tape somehow. And note that this Turing machine M always halts. Okay, so in order for it to be computing a function. So when we say a function f is computable, we mean there's a Turing machine which always halts and which converts input X into output f of X, basically. So it writes f of X on the tape. Then f is computable. Okay. And kind of informally in terms of programming languages, just if you can write a program, a subroutine with code that takes input X and gives output f of X, then f is computable. Okay, so so f being computable just means you don't just need to give a mathematical definition of a function mathematically just means a set of ordered pairs. F being computable means you need to describe code for how to implement that function. So you sort of it's sort of what a function would mean in programming languages, like a function in Python, the thing that starts with def something in Python or whatever. That's a function, I guess. That type of function, the one that computes something by giving code, and not then if the function is like that, then it's called a computable function. Okay. Whereas if your function is merely a set of ordered pairs, it's not necessarily computable. Okay, so just that's what we need, this notion of a function being computable to sort of here we give a definition in terms of Turing machine, but it's equivalent to the kind of less formal notion of when you can write code for the function. Okay, so this is the definition of a mapping reduction. Maybe you can just do a quick argument. So let's try to take this language, this language A. It has all the descriptions of Turing machines M, such that M halts when run on no input, when run on the inputs and empty string as input. When you run the M on the empty string as input, it halts. So then the task in A, to determine whether a string is in A, you basically want to determine whether a given code, a given machine, halts on the empty string or not. Okay, so it's similar to the halting problem, but the halting problem asks you whether a machine will halt on a given input W, and this just asks you whether a machine will halt on the empty string. Okay, so it's a special case of the halting problem. Okay, so if you could solve the halting problem, right? If you could decide the halting problem, then you could decide A. Okay, but now let's show the reverse direction. Let's try to show that if you can decide A, you can also decide the halting problem. That's actually the opposite of the easy direction, the opposite of the obvious direction. So we want to so basically, I guess my claim is that this direction is obvious. Okay, why? Because the reduction, the mapping reduction here, the function can basically just map it will just basically be this. So Well, okay, so technically when you're defining this function m, you have to deal with the misformatted inputs. So you can have to deal with f of x where x is not formatted like a Turing machine. So you can just give an output something that's not in HTM, so some fixed string that's not in HTM. You know, let's say y is a fixed string where y is some string not in HTM. Or actually, let's just to make it more simple, like it's something very, thinking something very explicit. Like let's suppose the string 1101 happens to not be in HTM. I don't know whether it is or not. It depends on how you encode Turing machines. But the point is, if this is if x is badly formatted. Okay, so if x is badly formatted, we'll just output some string, some fixed hard-coded string that's not in HTM. But otherwise, if the input is formatted like a Turing machine m, then we will output m comma epsilon. Okay, and then the idea is that this is a function from inputs to m to inputs to HTM essentially, and it's clearly computable because well, first you have to check whether the input is correctly formatted, but this can be checked pretty easily with a program. It's just a formatting check. Okay, and then if it's badly formatted, you just always output this one thing. If it's correctly formatted, then you just append this epsilon string. So that's also just something that's pretty easy to compute. So okay, so f is clearly computable. There's a program you can write that implements f. And then the goal, the point is that this is a mapping reduction. Why is it a mapping reduction? Basically because you know, this thing is in A if and only if this is in HTM. And this is basically by definition. Okay, that's basically just the definition of A. Okay, so it's pretty easy to see that this f is a matching direction. So this is the obvious direction. It's obvious that A is less difficult to decide basically than HTM. Okay, that there's a mapping reduction from A to HTM. That's the obvious direction. So if we want to show that A is undecidable, we actually want to show the opposite direction. So we actually want to show that HTM is less than A. So we want to show this. Okay. So let's show that. So we want so let's show this. So this is a bit trickier. So then, okay, how would we show this? Well, we want a mapping reduction f. Okay, so f will basically, let's ignore the badly formatted inputs. We know that we will do a format check. If it's badly formatted, we'll just always output something not in A. That's pretty easy. So let's ignore the badly formatted input. So then we know that the input looks like this. This is basically what a typical input to HTM looks like. Okay, so we want this, and we want it to basically be some m prime, or let's actually call it we want to call it some m sub w, and what we want this is m subscript w over there. So what we want is that mw run on epsilon halts if and only if m of w halts. You know, this way m of w would be in A if and only if mw is in HTM. You know, so basically, and this part is equivalent to saying that f of mw is in A. Okay, so then we get that this holds if and only if this, which is exactly the requirement we want. And we also want f to be computable. Okay, so we want to describe an algorithm that computes f. And also we want, so, but first we need to define this m sub w. Okay, we want m sub w when run on epsilon, we want that thing to halt if and only if m halts when run on w. Okay. All right. So, but of course, remember, we cannot determine whether m halts when run on w because that's solving the halting problem. So we want to construct this m sub w without actually figuring out whether m halts of w. Okay. And so the trick is that m sub w will be a Tm which writes W on the tape. So it has W hard coded in. It writes W on the tape, and then it runs M. Okay, so basically this Turing machine basically it hard codes W inside the description of the machine itself, and then it uses it uses something like about W or so extra states. It basically uses around that much extra states on top of the states of M in order to sort of hard code the string W. Okay, and then the first action of this new machine is to write down W on the tape, and then it basically runs M on what it wrote down. And so basically M sub W of epsilon, just behaves like M of W. So it writes W and then runs M. So it basically behaves just like M of W. So it halts if and only if M of W halts, which is what we wanted. Okay. So that's the trick. That's how you do mapping reduction there. And the conclusion you can get from it, so what we show formally in the notes, but what should kind of be intuitively clear if you think about it, is that, if A is less than B, is basically, and B is decidable, then A is decidable. So decidable, this word is decidable. Anyway, the point is that if A is less than or equal to B, it means A is easier than B. Okay, so here we showed, what we showed is that HTM is less than or equal to A here. In our case, HTM was less than or equal to A. That means HTM is easier than A to compute, to decide, or to recognize. Now, HTM we know is undecidable. Therefore, A must be undecidable. If A was decidable, then HTM would be decidable. Okay, so, oops, sorry, I just forgot the M subscript. Okay, so this actually proves that the language A that we wrote there is undecidable. The notes have a more formal version of this argument. Okay, so this is this mapping reduction is one way of showing that languages are undecidable. Sometimes you can prove reductions that are not mapping reductions, basically just a more general argument that says, suppose language B, suppose language B was decidable, suppose by contradiction. Now I will construct an algorithm that decides the halting problem. Therefore, that we get a contradiction. Okay, so that's we would more generally call this type of argument a reduction, roughly speaking, but it's not always a mapping reduction, right? So a mapping reduction is this one formal thing where you have this computable function. Okay, so the best way to show that a language is undecidable is to use some version of reduction. You don't have to reduce from the halting problem. You don't have to have the halting problem be your endpoint that says that you can use any other language is undecidable. So for example, we just showed that this language A is undecidable. The language A that was the set of all angle bracket M such that M of epsilon halts. We just showed this is undecidable just in this video. So if you want, you can use this as a kind of the contradiction point in your or to prove further reductions from it, basically. So you can say, okay, if language B is decidable, then we can get an algorithm for A, but that's a contradiction because A is undecidable. Therefore, language B, whatever your B is on a homework, say, therefore B is undecidable. Okay, so, and then as you encounter more and more undecidable languages, your kind of range of tools for your reductions, the things you can reduce from or to, grows. So in a sense, it becomes easier to prove new languages are also undecidable. Okay, that's all for now.